The formula is f of x is approximately L of x, L standing for linear. And the formula for L of x is f of a plus f prime of a times x minus a. I keep writing this equation over and over again. What is a? A could be lots of different things. Oftentimes it's 0 in many applications. Oftentimes a is 0. We did one example with the square root function last time. Let's do another example with the cube root function. Not the cube root of x. Let's do the cube root of, to make it a little bit complicated, maybe 8 plus 27x. Okay, so I'm making it a little bit complicated. It's usually not quite this complicated. Your problems are going to be a little simpler. I'd like to find you could phrase this in different ways. Sometimes it's phrased as find the tangent line approximation. Sometimes it's phrased as find the linear approximation. Sometimes it's phrased as find the local linearization. All three of those things mean the same thing. Tangent line approximation, linear approximation, local linearization. Find the local linearization. I'm going to use that one here. But that was kind of arbitrary. I could have said tangent line approximation. I could have said linear approximation. For f near x equals a, where I'm going to pick a to be 0. Again, that's the most common thing to pick for a in most examples that we encounter. It's not that it couldn't be something different. That's just the most common thing. I've got to use this formula. That's all I have to do. How? Well, I got to plug in a equals 0, first of all, into f, which I'll also write like this for ease of differentiation. And its derivative. F prime of x. What is its derivative? Take the derivative with the chain rule. Bring the 1/3 down. Subtract 1 from the exponent. Don't forget to multiply times the derivative of the inside function. And yeah, maybe it'd be good to simplify this a little bit. This simplifies to 9 over 8 plus 27x to the 2/3 power. Now just plug into this formula. F of x, which is this cube root function, purposely trying to make it a little bit more complicated than you encounter in your homework. Your homework's going to be easier than this, easier functions, is approximately L of x. Using a equals 0, that's going to be f of 0 plus f prime of 0 times x minus 0. Of course, multiplying by x minus 0 is the same as multiplying by x. F of 0 is the cube root of 8, which I purposely picked that to be a nice number. That's a 2. F prime of 0 is 9 over, plug in x equals 0. There you get 8 to the 2/3. That's a nice number as well. 8 to the 2/3 is 4. It's the cube root of 8 squared. 2 squared, 4. Times x. So this simplifies to 2 plus 9/4 x, or if you prefer decimals, that's 2 plus 2.25x. That's a function whose graph is the tangent line to the graph of this one at x equals 0. Do I happen to know what the graphs of these look like near x equals 0? I think I do. Based on my experience, I'm pretty sure the graph of f is going to look about like this. And the graph of the tangent line, well, if it's at x equals 0, it should look like that. Let's try it with the calculator and see. So it's, again, the cube root, which is the same as 1/3 power. I'll type 8 plus 27x in parentheses to the 1/3 power. I also want to graph this linear function 2 plus 2.25x. I want to plot them near x equals 0. I mean, I could try this window and see what it looks like. Actually, this cube root function is defined for all x, so I only graphed part of it. You can see the linear function does look like it's the tangent line at that point. If I zoom in closer to x equals 0, maybe negative 0.5 to positive 0.5, and y going from, say, 0 to 3, I'll see a nicer picture. There's that cube root function, and there's the tangent line. By the way, the cube root function does turn out to be not differentiable at whatever spot value of x where the slope happens to be infinite, which should occur, I believe, wherever this input is equal to 0, which would be x equals negative 8/27. I believe is where that has a vertical tangent. And it should work with approximations. For example, f of 0.1 should be approximately L of 0.1. 2 plus 2.25 times 0.1 is 2 plus 0.225 is 2.225. F of 0.1 in reality is the cube root of 8 plus 27 times 0.1 is 2.7. This is the cube root of 10.7 should be approximately that, 2.225. Let's try it and see. I'll try it with a cube root. We're just a 1/3 power here. 10.7 to the 1/3 power is hopefully not too far away from 2.225. Yeah, not terribly far away. Notice that the number we get from the linear approximation, 2.225, this one here, is a little bit bigger than the actual value. You should be able to explain why on a test. Really? How? Look at the graph. We just plugged in 0.1 into f, 0.1. The graph of f near that point is concave down, so the tangent line is above it. So when we use the tangent line to approximate it, we get an answer that's too big. 2.225 was a little bit too big. An overestimate. You also are going to have a problem or two or three where you have to think about error in the approximation. Error in the approximation. Not meaning you did anything wrong mathematically speaking, meaning you got an approximate answer, not an exact answer. That's what the error means. And I always remember this as actual value minus approximate value. And that's easy to remember because actual comes before approximate in a dictionary. Hey, do you know what a dictionary is? It's a big, thick book where the words are in order from alphabetical order. Okay. Alphabetical order, yeah. A, but C comes before P. I know you know as the dictionaries. The actual value is f of 0.1. The approximate value is L of 0.1. And this is, what do we get with the calculator? 2.204 is an approximate actual value, still not the exact actual value, minus the 2.225. 2.204 minus 2.225. We get an error of negative 0.021. Yes, errors can be negative. When the approximation is a bit too big, the error is negative. because you're subtracting a bigger number from the actual. Seems a little strange, but that's the way it goes. Approximations that are too big correspond to negative errors. Approximations that are too small correspond to positive errors. It is a good idea to keep track of the sign of the error, positive or negative sometimes. It's also important to realize that this error in the approximation could work no matter what x is. In general, this error, this approximation error, is the actual value minus the approximate value. That's f of x minus L of x for any x. So for this example, that's the cube root of 8 plus 27x minus, in parentheses, 2 plus 2.25x. And yes, I could distribute the minus sign through the parentheses. And since I can do that for any x, this is really a function of x, error of x. Wild. And since it's a function of x, I could graph it. Wild. What does the graph look like? I won't take the time to do it on the calculator, but what the graph would look like in this case is this. It would kind of look like an upside down parabola. It would not technically be a parabola, but it would look similar. I just happen to know. On a certain scale, you'd get a graph that looks like that. Notice the error at x equals 0 is 0. F of 0 minus L of 0 is 0. They're the same. F of 0 is the cube root of 8, 2. L of 0 is 2. 2 minus 2 is 0. It's also close to 0, but negative when x is close to 0. And here's another important thing about it. It looks like it's got a slope of 0 there, a derivative of 0 there. That's actually important. But just realize that that happens for the moment. I'll talk more about this a little bit on Friday. But you do have a homework problem or two where you have to think about this error as a function of x. Just use your technology to graph it.